What if I told you that the greatest mysteries of the universe don't lie in the distant galaxies or swirling nebulae we marvel at through telescopes, but in particles so small, they're invisible to even the most powerful microscopes? Picture this. Every star, every planet, every ripple in the fabric of space is shaped by forces happening on a scale a billion times smaller than a grain of sand. These are the hidden architects of reality, the quantum dancers whose movements dictate the fate of the cosmos. And today, we're pulling back the curtain on their extraordinary influence. Think about the last time you looked up at the night sky, awestruck by its vastness. That sense of wonder, it's only half the story. Because while we're drawn to the grand spectacle of supernovas and black holes, the true magic happens in the silent, unseen world of subatomic particles. Dark matter, ghostly neutrinos, and quantum fluctuations, these aren't just abstract concepts. They're the invisible hands molding galaxies, bending light, and even stretching the very fabric of time. Scientists are just beginning to unravel how these tiny entities hold sway over the largest structures in existence. And what they're discovering is rewriting the rules of physics as we know them. So how does the cosmic microcosm, this realm of the unimaginably small, steer the destiny of the universe? That's the journey we're about to take together. From the bizarre behavior of particles that defy logic to the hidden dimensions that might exist all around us, we'll explore how the smallest building blocks of reality shape the grandest cosmic phenomena. By the end of this exploration, you won't just see the universe differently, you'll understand it differently. Because once you peer into the quantum world, you realize the cosmos isn't just out there. It's in everything, connecting the infinitesimal to the infinite in ways that will leave you breathless. Ready to dive in? Let's begin. To grasp just how strange and unstable the foundation of our universe truly is, we need to zoom in way in past atoms, past electrons, even past the tiniest quarks, to a realm where the very concept of empty space dissolves into chaos. This is the quantum foam, a seething ocean of energy where particles flicker into existence for mere fractions of a second before vanishing again, like bubbles bursting in a cosmic soda. It's as if spacetime itself is boiling at its core, with every square inch of the universe fizzing with these ghostly particles. The wildest part, they're not just passive spectators. These fleeting disturbances might actually tug at the fabric of gravity, subtly warping the universe from the bottom up. Think of it like a trampoline. At first glance, it looks smooth and still, until you notice ants scurrying across its surface. Each tiny movement sends ripples through the material, bending it imperceptibly. Now imagine those ants are quantum particles and the trampoline is spacetime itself. That's the quantum foam in action, an endless dance of energy that could be bending the rules of reality. John Wheeler, the visionary physicist who first described this phenomenon, realized that if these fluctuations are real, they might solve some of cosmology's biggest puzzles. Black holes, for instance, could owe their immense gravitational pull not just to their mass, but to the churning quantum chaos at their cores. Even wormholes, those hypothetical cosmic shortcuts, might owe their existence to these microscopic whirlpools in spacetime. But how do we know any of this is real? The clues come from some of the most delicate experiments ever devised. Scientists have observed particles behaving in ways that defy classical physics, as if they're being nudged by invisible forces. There are even theories suggesting that dark energy, the mysterious force accelerating the expansion of the universe, might be fueled by the relentless bubbling of the quantum foam. If true, it would mean the largest and smallest scales of existence are locked in an eternal feedback loop, each shaping the other in ways we're only beginning to decode. So the next time you gaze at the night sky, remember, the vast silence of space is an illusion. Beneath the calm, there's a storm raging, one that might hold the keys to everything from the birth of galaxies to the fate of the cosmos itself. Dark matter is the universe's best-kept secret, an invisible force weaving through the cosmos, holding galaxies together like cosmic glue. Picture a spider's web, delicate yet impossibly strong, its threads unseen until dew catches the light. That's dark matter, undetectable, yet its gravitational fingerprints are everywhere. Take our own Milky Way. Stars on the outer edges whirl around the galactic center so fast that, by all rights, they should fling off into the void like marbles spinning off a plate. But something unseen, something massive, keeps them tethered. That something is dark matter, a shadowy scaffold wrapping around galaxies, keeping them from flying apart. What makes this mystery even stranger is what dark matter is. It doesn't glow like stars, absorb light like dust, or collide with planets like asteroids. It's utterly silent, passing through you right now as if you weren't even there. Scientists call these hypothetical particles WIMPs, weakly interacting massive particles, because they barely acknowledge ordinary matter's existence. Or perhaps dark matter is made of axions, particles so lightweight they flutter through the cosmos like quantum whispers. Either way, their elusiveness is maddening. We only know they exist because of their gravity. When light from distant galaxies bends unnaturally, or stars orbit faster than math predicts, dark matter is the ghost in the equations, the missing piece we can't see but can't ignore. The hunt for dark matter has turned science into a cosmic detective story. Underground labs shielded from cosmic rays listen for the faintest ping of a WIMP colliding with an atom. Space telescopes map the distorted light of distant galaxies, tracing dark matter's gravitational fingerprints. Even the Large Hadron Collider smashes particles at near-light speeds, hoping to shake loose a clue. Yet after decades, dark matter remains just out of reach, like a shape glimpsed in peripheral vision that vanishes when you turn your head. But here, the breathtaking part. Without dark matter, the universe would be unrecognizable. Galaxies wouldn't have clumped together in the early cosmos. Stars might never have ignited. The night sky, instead of glittering with spirals and clusters, would be a vast, empty scattering of lost suns. Dark matter isn't just a puzzle, it's the architect of everything we see. And that raises a humbling question. What if the majority of reality isn't just hidden, but operates by rules we've yet to imagine? The answer could rewrite not just physics, but our very understanding of existence. If you could see the hidden traffic of the universe, your body would light up like a cosmic highway, not with stars or comets, but with trillions of ghostly particles called neutrinos streaming through you every moment. These phantoms of the subatomic world are born in the most violent stellar events. Supernovae exploding with the energy of 1 billion suns, nuclear furnaces blazing at the cores of stars, even the Big Bang's fading echo. Yet despite their staggering numbers, neutrinos glide through planets like they're made of air, leaving barely a trace. In fact, out of those trillions passing through your hand right now, maybe, just maybe, one will collide with an atom in your entire lifetime. This eerie ability to slip through matter untouched makes neutrinos cosmic messengers, carrying secrets from the universe's most extreme environments. Take the IceCube Observatory in Antarctica, where scientists have buried thousands of sensors deep in glacial ice, turning a cubic kilometer of the South Pole into a neutrino telescope. When one of these rare particles finally does interact, it creates a fleeting streak of blue light, a signal so faint it's like trying to spot a firefly in a blizzard. But these whispers from space reveal astonishing things. The inner workings of collapsing stars, the particle showers near black holes, even echoes of the early universe. But neutrinos aren't just passive travelers. They might hold the answer to one of physics' greatest mysteries. Why does anything exist at all? According to the Big Bang, matter and antimatter should have annihilated each other in a burst of energy, leaving behind an empty cosmos. Yet here we are. Neutrinos could be the key. Some theories suggest these particles behave differently than their antimatter counterparts, tipping the scales ever so slightly in favor of matter. It's as if the universe played a game of dice trillions of times, and neutrinos were the tiny weight that made all the difference. And then there's the real shocker. Neutrinos refuse to follow the rules. The standard model of physics, our playbook for how particles behave, predicts they should be massless. but experiments prove they have mass, just an impossibly tiny amount. This discrepancy cracks open the door to entirely new physics, hinting at dimensions or forces we've yet to discover. Some scientists even speculate that neutrinos, despite their ghostly nature, could be sculpting the cosmos on a grand scale. Their collective gravity might nudge galaxies into clusters or influence the universe's expansion. So while we chase dark matter and quantum foam, neutrinos remind us that the smallest players often have the biggest roles. They're the universe's silent witnesses, the shadows flitting through walls of lead, the particles so elusive they redefine what it means to be, and in their quiet way, they might be writing the next chapter of physics itself. Cosmic rays are the universe's ultimate speed demons, atomic fragments hurtling through space at nearly the speed of light, packing energies so immense they dwarf anything scientists can create in particle colliders. Imagine a single proton, smaller than an atom, carrying the punch of a major league fastball. These particles don't just travel, they rage across the cosmos, born in the most extreme environments imaginable. The shockwaves of exploding stars, the swirling disks of supermassive black holes, even the violent hearts of distant quasars. And when they slam into Earth's atmosphere, they unleash fireworks of secondary particles in sprawling, invisible avalanches called air showers. A phenomenon so dramatic it's as if the sky itself is cracking open. But here's what's truly wild. Cosmic rays might be shaping our world in ways we're only beginning to understand. Some scientists suspect these high-energy visitors could seed clouds by ionizing molecules in the atmosphere, potentially altering weather patterns over. There's even a controversial theory that cosmic rays played matchmaker in the story of life itself, their collisions triggering mutations in ancient DNA that accelerated evolution. Picture this, a single particle from a dying star, traveling billions of years across interstellar space, only to nudge the genetic code of some primordial microbe, a cosmic spark in the chain of events that led to us. The hunt to trace these particles back to their origins is like piecing together a galactic crime scene. When cosmic rays reach us, their paths are scrambled by magnetic fields, leaving no obvious trail home. So physicists get creative. The Pierre Auger Observatory in Argentina uses 1,600 water tanks spread over an area the size of Ireland to catch the faint afterglow of air showers. Meanwhile, space telescopes like Fermi scan the skies for gamma rays, the telltale flashes created when cosmic rays collide with interstellar gas. Together, these clues hint that some of the most energetic rays might come from active galactic nuclei, where black holes spew jets of plasma stretching millions of light years. Yet the biggest puzzle isn't just where cosmic rays come from, it's how they reach such impossible energies. The most powerful ones, dubbed "oh my god" particles, carry the kinetic energy of a bowling ball dropped from waist height, but concentrated into a single subatomic speck. Nothing in our current physics can fully explain their acceleration. Some theories point to shockwaves in supernova remnants acting as natural particle accelerators, while others suggest they're flung across the cosmos by collapsing magnetic fields around neutron stars. But the truth might be stranger. Could there be cosmic factories out there, unknown phenomena, pumping particles to energies that defy logic? What's certain is this: every time a cosmic ray streaks through your body, it's a whisper from the universe's most violent corners. These tiny messengers connect us to supernovae we'll never see, black holes we'll never visit, and forces we've yet to name. They remind us that the universe isn't just something we observe, it's something we're part of, a grand conversation between the infinitesimal and the infinite, written in particles older than the stars. The universe has a silent partner in the business of existence, an invisible field that fills every corner of space, shaping the very nature of reality. This is the field, a cosmic molasses that gives mass to particles simply by being there. Picture wading through a pool of honey. The thicker the liquid, the harder it is to move. Now imagine that honey is everywhere, even in the vacuum of space, and instead of slowing you down, it's what gives you substance. That's how the field works. When particles interact with it, they acquire mass, some trudging through like elephants in tar, others slipping by like minnows through water. Electrons, quarks, even the building blocks of atoms owe their weight to this unseen force. Without it, everything would zip around at the speed of light, never clumping together to form stars, planets, or us. The discovery of the boson in 2012 was like finding the fingerprint of this field, a ripple in the cosmic fabric that proved its existence. Scientists at the Large Hadron Collider spent decades smashing protons together at nearly light speed, hoping to catch a glimpse of this elusive particle. When they finally did, it wasn't just a triumph of engineering, it was a revelation. The boson was the missing piece of the Standard Model, the rulebook for how particles behave. But here's the twist. The field doesn't just explain mass, it might hold clues to the universe's most explosive secret. Some theories suggest that in the first fractions of a second after the Big Bang, the field wasn't steady. It could have been a seething, unstable energy, like water superheated in a microwave, just waiting to bubble over. When it finally settled into its current state, that transition might have released an unimaginable surge of energy, inflating the universe faster than light in a process called cosmic inflation. In other words, the field could be the match that lit the fire of creation. But the story gets even stranger. The field isn't just a relic of the past, it's still alive, still dynamic. Calculations show it's hovering in a delicate balance, like a pencil standing on its tip. If it were to shift again, even slightly, the consequences would be catastrophic. A new phase transition could rewrite the laws of physics, altering the mass of particles so drastically that atoms would disintegrate, stars would blink out, and reality as we know it would unravel. It sounds like science fiction, but the math suggests it's possible. The universe might be sitting on a knife's edge, with the field holding everything together for now. So what does this mean for the future? Some physicists speculate that if the field is metastable, balanced precariously but not permanently, a random quantum fluctuation could trigger its collapse. The good news, if it happens, it would spread at the speed of light, meaning we'd never see it coming. The better news, the odds are astronomically low, at least for billions of years. But the mere possibility forces us to confront a humbling truth. The universe isn't just stranger than we imagine. It's stranger than we can imagine. The field isn't just a footnote in physics. It's the invisible hand that shaped the cosmos, and its mysteries are far from solved. Perhaps the most astonishing thought of all is that this field, which dictates the mass of every particle in existence, might also be the key to understanding why there's something rather than nothing. From the birth of the universe to the fate of reality itself, the field is more than a scientific curiosity. It's the silent architect of everything. And as we continue to probe its secrets, we're not just exploring physics, we're uncovering the very rules of existence. Quantum entanglement is the universe's ultimate magic trick, a connection so profound it makes distance irrelevant. Imagine tossing a pair of gloves into opposite ends of the galaxy. Open one to find a left hand, and instantly, without any signal or delay, you know the other is a right. That's entanglement in action. Particles born together or interacting in just the right way become permanently linked, their fates intertwined no matter how far apart they drift. Famously dismissed this as spooky action at a distance, refusing to believe reality could operate this way. Yet experiment after experiment has proven him wrong. When scientists measure one entangled particle's spin, polarization, or other quantum property, its partner snaps into a correlated state faster than light could travel between them. It's as if the universe cheats, skipping the middleman of communication entirely. But how does this defy physics? Classically, information can't travel faster than light. It's one of relativity's sacred rules. Entanglement doesn't just bend that rule, it shatters it. Yet here's the catch. While the correlation is instantaneous, we can't use it to send messages. It's like having twin dice that always land on matching numbers but no way to force a specific result. This subtlety keeps causality intact, but the implications are still staggering. Take quantum cryptography, where entangled particles create unbreakable codes. Any attempt to eavesdrop disrupts their delicate connection, alerting users to interference. Or quantum computing, where entangled qubits perform calculations at speeds impossible for classical machines, solving problems like drug discovery or climate modeling in days instead of. The real mind-bender, entanglement might not stop at tiny particles. Some physicists speculate it could scale up to cosmic proportions, weaving hidden threads through spacetime itself. Picture the universe's large-scale structure, galaxies clustered in vast filaments like foam on an ocean. What if entanglement, operating since the Big Bang, subtly guided this architecture? There's even a wild theory called entanglement gravity, suggesting that what we perceive as gravity could emerge from countless quantum connections between particles, like a cosmic net holding matter together. If true, it would mean two great legacies, relativity and his skepticism of quantum weirdness, might someday reconcile in the most unexpected way. Yet the most haunting question remains: how? How can particles know each other's states across light years? One radical idea is that entanglement reveals a deeper layer of reality where separation is an illusion. Think of spacetime as a hologram, its 3D appearance projected from a 2D boundary where all points are fundamentally connected. In this view, entanglement isn't spooky. It's the universe reminding us that distance, as we understand it, might be a trick of perception. Every time we confirm entanglement in labs, whether with photons shot through mountain tunnels or satellites beaming pairs of particles to opposite continents, we chip away at classical intuition. The universe, it seems, prefers entanglement's strange choreography to the rigid clockwork Newton imagined. And as we peer deeper, we might find that this quantum glue doesn't just bind particles, it binds the cosmos. Even the emptiest void in the universe is anything but empty. Quantum mechanics reveals that what we call nothing is actually a seething, bubbling cauldron of activity, where particles and antiparticles constantly wink in and out of existence like fireflies in the dark. These are virtual particles, ghostly pairs that borrow energy from the vacuum itself, existing just long enough to obey uncertainty principle before vanishing back into the cosmic ledger. It's as if space itself has an unlimited credit line, and these particles are fleeting transactions, debts incurred and repaid in fractions of a nanosecond. But don't let their ephemeral nature fool you. Virtual particles leave fingerprints everywhere. Take the effect. Place two metal plates incredibly close together in a vacuum and they'll inexplicably pull toward each other. Why? Because the narrow gap between them limits the types of virtual particles that can form there, creating a pressure imbalance. Outside the plates, the quantum foam froths freely, but inside it's stifled. The result: a measurable force emerging from what we'd call empty space. Proof that these phantom particles are more than mathematical abstractions. Then there's Hawking radiation, perhaps the most dramatic demonstration of virtual particles' power. At the edge of a black hole's event horizon, gravity is so intense it can tear a virtual particle pair apart before they annihilate. One particle falls into the abyss while the other escapes as real radiation. Over eons, this slow leak drains the black hole's energy, causing it to evaporate. Think about that. The universe's most voracious monsters are slowly dissolving, thanks to quantum flickering at the very edge of reality. What's truly unsettling is how this challenges our definition of something versus nothing. If virtual particles can emerge from the void, interact with the world, and even alter the fate of black holes, then the vacuum of space isn't passive. It's dynamic, creative, almost alive. Some theories suggest dark energy, the force accelerating the universe's expansion, might be fueled by vacuum fluctuations, a kind of quantum interest on all that borrowed energy. Others speculate that virtual particles could have played a role in the Big Bang itself, with the universe arising from a primordial quantum fluctuation writ large. The implications spiral even further when you consider that virtual particles might not be limited by time. In quantum field theory, particles can briefly travel backward in time as easily as forward, appearing as antiparticles in diagrams. This means the vacuum's dance isn't just happening in space, it's threaded through time itself, a four-dimensional tapestry of creation and destruction. So the next time you stare into the night sky, remember, the vast darkness isn't empty. It's a quantum stage where particles perform an endless, invisible ballet, shaping everything from the fate of stars to the fabric of space-time. And if we've learned anything from this, it's that the universe thrives on borrowed energy, dancing on the edge of nothingness in ways we're only beginning to comprehend. The vacuum catastrophe is one of physics' most jarring wake-up calls, a glaring mismatch between what our equations insist should be and what the universe actually does. According to quantum field theory, empty space isn't empty at all. It crackles with virtual particles that collectively generate a background energy density. Calculate this energy by summing up all those fleeting quantum fluctuations, and the result is staggering. The vacuum should possess around 120 orders of magnitude more energy than what astronomers measure. That's like predicting a tsunami and finding only a ripple in a teacup. This discrepancy isn't just a rounding error. It's a chasm so vast it threatens to swallow our understanding of cosmology whole. So where does this cosmic math go wrong? The trouble starts with how we define nothing. Classical physics imagined the vacuum as a true void, but quantum mechanics paints it as a frenetic marketplace where particles constantly trade borrowed energy. Every cubic centimeter of space, even in the deepest void between galaxies, is theorized to contain enough of this zero-point energy to boil oceans. Yet when we observe the universe's expansion, measured through distant supernovae, galaxy clustering, and the cosmic microwave background, the actual vacuum energy is almost negligible. The cosmological constant, lambda, is so tiny it's as if the universe forgot to inflate its own balloon. Desperate to bridge this gap, physicists have proposed some radical fixes. Supersymmetry, an elegant but still unproven theory, suggests every known particle has a hidden twin. If these superpartners exist, their contributions to vacuum energy might perfectly cancel out the quantum noise, leaving behind the faint residue we observe. Others turn to string theory's extra dimensions, where gravity and perhaps vacuum energy could leak into hidden realms, diluting their apparent strength in our four-dimensional world. Then there's the controversial anthropic principle, which argues that universes with higher vacuum energy would expand too violently for stars or life to form. In this view, we only observe a small lambda because we couldn't exist in a more energetic vacuum. But the boldest ideas question whether dark energy is even constant. What if it's a dynamic field, slowly fading over time? Or what if the vacuum's energy isn't fundamental but emergent, a statistical illusion like temperature, arising from deeper quantum connections we haven't yet uncovered? The stakes couldn't be higher. If the vacuum held the energy quantum mechanics predicts, galaxies would have been torn apart before they could form. The fact that we're here to ponder this means something. Some mechanism, some symmetry, some undiscovered law is holding reality in precarious balance. This isn't just academic curiosity. The vacuum catastrophe cuts to the heart of the universe's fate. Will dark energies whisper-thin push fade, letting gravity pull everything back in a big crunch? Or will it prevail, dooming the cosmos to an eternal, frozen expansion? Right now, we're like cartographers trying to map an ocean we've only glimpsed through fog. Until we solve the riddle of the vacuum's missing energy, the universe's ultimate destiny remains a story with the last page torn out. Supersymmetry is the universe's ultimate balancing act, a theory so elegant it could solve half of physics' greatest mysteries with a single stroke. Imagine a cosmic mirror where every particle we know, quarks, electrons, photons, has a hidden twin, a heavier superpartner lurking just beyond our current reach. These shadow particles wouldn't just be curiosities. They'd be the missing links in a grand unification, tying together forces, stabilizing the field, and even accounting for dark matter's invisible bulk. It's as if nature, in its infinite creativity, designed a hidden layer to reality, one that smooths out the rough edges in our equations and answers questions we haven't even fully asked yet. Take the hierarchy problem. Why is the boson so improbably light? Quantum correction should inflate its mass to scales trillions of times larger, rendering atoms, and by extension us, impossible. But supersymmetry's mirrored particles cancel out these corrections with near-perfect precision, like two dancers moving in flawless opposition. If SUSY is real, it wouldn't just explain it'd suggest the universe is fine-tuned not by accident, but by mathematical necessity. Even dark matter could be a relic, with hypothetical superpartners, floating unseen through galaxies, their collective gravity stitching the cosmos together. Yet for all its promise, supersymmetry remains frustratingly out of reach. The Large Hadron Collider has scoured collision data for signs of these superpartners, from to squarks, but so far the detectors have stayed silent. This absence doesn't kill SUSY, but it forces physicists to ask hard questions. Are superpartners simply heavier than we thought, hiding in energy ranges the LHC can't yet probe? Or is nature more inventive, weaving dark matter and unification from threads we haven't even imagined? Some theorists cling to hope, tweaking SUSY models to push predictions beyond current limits. Others wonder if we're witnessing a paradigm shift, where the answers lie not in symmetry, but in something entirely new: extra dimensions, holographic principles, or quantum entanglement on cosmic scales. What's at stake isn't just a footnote in particle physics. If supersymmetry is confirmed, it would rank among the greatest scientific breakthroughs since relativity, rewriting textbooks from the ground up. If it's disproven, the implications are just as profound. The universe's fine-tuning might demand explanations far stranger than we've dared to consider. Either way, the hunt for SUSY is more than a test of one theory. It's a referendum on how deeply symmetry shapes reality. And as colliders grow more powerful and telescopes peer further back in time, we might soon discover whether the cosmos dances to supersymmetry's hidden rhythm, or if the music we're hearing is something altogether different. String theory rewrites the script of reality at its most fundamental level, not with point-like particles, but with infinitesimal threads of energy vibrating in an 11-dimensional symphony. Picture a guitar string. Pluck it one way and you get a bass note, another way a high-pitched chime. Now imagine those strings are a billion times smaller than an atom, their vibrations not creating music but shaping the very fabric of matter. An electron, just a string vibrating at a particular frequency. A quark, another harmonic. Even gravity emerges from this cosmic orchestra with the graviton, the hypothetical carrier of gravitational force, as a specific resonant mode. It's a vision so unifying that it could dissolve the century-old feud between quantum mechanics and general relativity, stitching spacetime and the quantum world into a single, elegant tapestry. But why extra dimensions? Think of a power line stretching to the horizon. From afar, it looks like a one-dimensional thread, but up close, you realize it's a cylinder wrapped around a hidden axis. String theory suggests our universe might be similar, with 6 or 7 dimensions curled into spaces smaller than a quark, their geometry dictating how strings vibrate and interact. These hidden folds could hold answers to physics' biggest puzzles. Black holes, for instance, might reveal their mysterious entropy through strings dancing on their event horizons, counting the quantum microstates that define their chaos. The Big Bang itself could have been a cataclysmic collision of higher dimensional membranes, a cosmic reboot echoing through the dimensions we perceive. Yet for all its mathematical beauty, string theory faces a formidable challenge: proof. The energy scales required to directly observe strings are trillions of times beyond our most powerful colliders, leaving the theory stranded in a sea of untestable elegance. Critics argue it's less a science than a philosophy, a dazzling castle in the air with no foundation in experiment. But supporters counter that absence of disproof isn't disproof. After all, gravitational waves were once deemed unmeasurable, and neutrinos seemed forever elusive. The James Space Telescope now peers back to the universe's infancy, hunting for gravitational imprints of cosmic strings, hypothetical relics from the early universe that could serve as string theory's smoking gun. Perhaps the most tantalizing clue lies in the AD-SCFT correspondence, a theoretical bridge linking string theory in a warped five-dimensional space to a four-dimensional quantum field theory. This holographic principle suggests our 3D reality might be a projection of information encoded on a distant boundary, like a movie playing on the surface of a bubble. If true, it would mean the universe isn't just described by mathematics. It is mathematics, a self-consistent structure where strings and their vibrations are the ultimate code. So while string theory remains a silhouette against the unknown, its ambition is undeniable. It dares to ask not just how the universe works, but why it works this way, and in doing so offers a glimpse of a reality far stranger, richer, and more interconnected than we ever dreamed. Whether the strings are real or merely a beautiful mirage, their song continues to echo through the halls of physics, challenging us to listen deeper. The holographic principle turns our perception of reality inside out. What if the three-dimensional universe we experience is just a grand illusion, a cosmic mirage projected from information etched on a distant two-dimensional surface? This isn't science fiction. It's a serious hypothesis born from the most perplexing puzzles in physics. Take black holes, those cosmic paradox machines. When matter falls into one, it seemingly vanishes forever, violating quantum mechanics, rule that information can never be destroyed. But in the 1970s, physicist Jacob calculated that a black hole's entropy, a measure of its hidden information, is proportional not to its volume but to the area of its event horizon. It's as if all the data about what fell in is smeared across the surface, like a celestial hard drive. Stephen Hawking later showed that black holes slowly evaporate, radiating away their mass. But if the information inside isn't lost, where does it go? The holographic principle offers a jaw-dropping answer. It was never inside to begin with. Think of a hologram, those shimmering images where a 3D object seems to float in space, even though it's encoded on a flat film. Shine light through the film and the illusion emerges. The holographic principle suggests spacetime works the same way. The universe's true source code might live on a boundary we can't see, perhaps at the edge of the observable cosmos or woven into the fabric of scale physics. Every star, every galaxy, even your own thoughts could be pixels in a vast cosmic projection. This idea gained mathematical muscle in the late 1990s, when physicists discovered the AD-SCFT correspondence. A concrete example where a higher dimensional space, in this case, a warped five-dimensional universe, is perfectly described by a lower dimensional quantum field theory on its boundary. It's like finding a DVD that somehow contains not just a movie, but the entire theater, the audience, and the smell of popcorn, all encoded in flat, swirling data. But how could this possibly work in our universe? One clue lies in how information scales. In ordinary physics, the entropy of a system grows with its volume, more space, more possible states. But in holographic models, entropy maxes out at the bounding area, as if the universe has a hidden pixel limit. This aligns with bizarre findings in quantum gravity, where spacetime itself seems to break down into indivisible-sized units when you zoom in far enough. Imagine your computer screen. From a distance, images appear smooth, but up close, you see the pixels. The holographic principle hints that spacetime has a similar granularity, with each pixel carrying a bit of information that collectively generates the illusion of depth. The implications are staggering. If the universe is a hologram, then time and space aren't fundamental. They're emergent phenomena, like temperature arising from the motion of atoms. Quantum entanglement, that spooky connection between particles, might simply be threads linking data points on the cosmic projector. Even the Big Bang could be reinterpreted as a moment when the hologram's resolution switched on, transforming a flat, hot code into the expanding 3D reality we inhabit. Yet the hardest part isn't the math, it's the existential whiplash. How do we reconcile the solidity of a mountain, the warmth of sunlight, the vastness of the night sky, with the idea that it's all on the universe's deepest layer? Perhaps the answer lies in recognizing that reality has always been more about relationships than absolutes. A hologram isn't less real because it's projected. It's just real in a different way. And if the universe whispers its secrets not in 3 dimensions, but in 2, we're left with a humbling thought. The greatest show in existence might be playing on a screen we've yet to fully see. Black holes aren't just cosmic vacuum cleaners. They're the universe's ultimate shredders, swallowing stars, planets, and light itself with no apparent way to retrieve what falls in. But here's the crisis. Quantum mechanics insists that information can never truly be destroyed. Every particle's spin, charge, and history must persist in some form, even if scrambled beyond recognition. So when a black hole devours a star, does that star's information vanish forever? Stephen Hawking once thought so. His groundbreaking work showed that black holes slowly leak energy, Hawking radiation, eventually evaporating into nothingness. But if the radiation is random, as Hawking initially believed, then the information locked inside would be erased, violating quantum law. This contradiction became the black hole information paradox, a puzzle so deep it forced physicists to question the bedrock of reality. The stakes couldn't be higher. If information can disappear, it undermines quantum theory's core principle of unitarity, the idea that the universe keeps perfect track of every bit's journey. Imagine burning a book and claiming its story could still be read in the smoke's pattern. That's the level of absurdity physicists faced. But recent breakthroughs suggest the universe might have a cosmic backup system. One leading idea is that Hawking radiation isn't random after all. Instead, it could be subtly imprinted with data from the black hole's interior, like a scrambled radio signal waiting to be decoded. Picture the event horizon as a quantum firewall, a turbulent boundary where incoming matter's information gets smeared across the surface, then slowly re-emitted in the radiation. It's as if the black hole is a celestial hard drive, encrypting data into thermal noise. Even stranger, the holographic principle offers a way out. If the universe is fundamentally two-dimensional, a projection of data stored on some distant boundary, then the information swallowed by a black hole might never have truly entered it. Instead, it could remain encoded on the black hole's surface like a holographic sticker. This aligns with T. and Bold's conjecture. Black holes don't destroy information, they store it in the most counterintuitive way possible. Recent simulations using quantum computers have added weight to this view, showing how information could survive evaporation by becoming entangled with the outgoing radiation. Yet mysteries linger. If information escapes, how does it bridge the gap between the black hole's interior and exterior without violating relativity's speed limit? Some theories invoke wormholes, quantum threads threading through spacetime, connecting the radiation to the lost matter. Others propose that spacetime itself is built from quantum entanglement, meaning the paradox reveals a flaw in how we perceive separation. Every potential solution points to something profound. The universe might be far more interconnected, far more clever than we ever imagined. What's clear is this: the information paradox isn't just about black holes. It's a stone for decoding how gravity and quantum mechanics fit together. Unravel it, and we might finally glimpse the universe's deepest operating system, a place where nothing is ever truly lost, only transformed. Dark energy is the universe's greatest unsolved riddle. an invisible force pushing galaxies apart faster and faster, as if space itself has a hidden accelerator pedal. Picture a balloon not just inflating, but stretching so rapidly that the dots on its surface race away from each other at ever-increasing speeds. That's our cosmos hurtling toward an uncertain future, with dark energy calling the shots. We know it exists because of distant supernovae, exploding stars whose light is fainter than expected, betraying the universe's accelerating expansion. Yet for all its dominance, making up nearly 70% of the universe's energy budget, dark energy leaves no fingerprints, no trails, no direct clues to its identity. The simplest explanation is cosmological constant, a fixed energy density woven into the fabric of space itself. Think of it as a background hum, a uniform pressure that never fades or fluctuates. But there's a problem. When physicists calculate how much energy the quantum vacuum should contain, the result is a number 10 to the power of 120 times too large. If dark energy were truly this constant, galaxies would have been ripped apart before they could even form. So is it a fudge factor, a placeholder for something far stranger? Some theorists propose quintessence, a dynamic field that ebbs and flows over time, potentially weakening or strengthening as the cosmos evolves. Others wonder if dark energy is an illusion, a sign that gravity needs rewriting on cosmic scales. Modified gravity theories like MOND suggest that what we perceive as acceleration might actually be gravity behaving differently across vast distances. Then there's the quantum connection. Could dark energy be fueled by the same virtual particles that flicker in and out of existence in the vacuum? If so, it would mean the universe's expansion is driven by the restless churn of nothingness itself, a cosmic engine running on borrowed energy. But why is the effect so subtle? Why doesn't quantum chaos tear spacetime apart? The answer might lie in a cancellation mechanism we haven't discovered yet, some symmetry or hidden variable that tames the vacuum's wild tendencies. The stakes couldn't be higher. If dark energy strengthens over time, it could trigger a big rip, a catastrophic end where galaxies, stars, even atoms are torn asunder by runaway expansion. If it weakens, gravity might regain control, pulling everything back in a fiery collapse. Or perhaps the universe will continue its lonely, silent expansion, fading into darkness as the last stars wink out. Right now, telescopes like the Observatory and Euclid Space Telescope are mapping billions of galaxies, searching for patterns that might reveal dark energy's true face. Every supernova, every distortion in the cosmic web is a clue in this grand detective story. One thing's certain, dark energy isn't just a mystery. It's the architect of the universe's destiny, the invisible hand shaping everything from the largest galaxy clusters to the fate of time itself. And as we peel back its layers, we're not just exploring space, we're unraveling the very rules of existence. Imagine the universe in its first sliver of existence, smaller than an atom, hotter than the core of a star, and suddenly, it explodes. Not with fire or sound, but with space itself stretching faster than light can chase it. This is cosmic inflation, the universe's most dramatic growth spurt, where in less than a trillionth of a second, the cosmos ballooned from subatomic to cosmic scales. But what could possibly power such an outrageous expansion? Enter the field, a mysterious energy saturating the infant universe, acting like an unstoppable anti-gravity force. Picture a ball rolling down an impossibly steep hill, except the hill is made of pure potential energy, and as the ball rolls, space itself stretches beneath it exponentially. Inflation solves some of cosmology's most stubborn puzzles. Look at the night sky. No matter where you point a telescope, the universe looks eerily uniform, with galaxies distributed in a near-perfect cosmic web. Without inflation, regions now billions of light years apart could never have exchanged heat or information, yet they share identical temperatures down to 1,000th of a degree. It's like walking into a concert hall where every musician, without rehearsal, plays the same note flawlessly. Inflation's breakneck expansion stretched quantum ripples into cosmic wrinkles, tiny variations in density that gravity later sculpted into galaxies and voids. Those imperfections are frozen in the cosmic microwave background, the afterglow of the Big Bang, where satellites have mapped them with breathtaking precision. But the wildest twist isn't just how inflation started, it's how it might have ended. When the field's energy finally decayed, it didn't just fade away. It reheated the universe, transforming its potential energy into a firestorm of particles, lighting the fuse for stars, planets, and eventually us. This moment, called reheating, was the universe's true birthday party, the instant matter as we know it was born from pure energy. Now here, where it gets speculative. Could inflation be more than a one-time event? Some theories suggest our universe is just one bubble in an endless cosmic foam, where new universes constantly bud off from quantum fluctuations in an eternal inflating background. If true, the multiverse isn't science fiction. It's a natural consequence of quantum fields doing what they do best, fluctuating unpredictably. Each bubble universe could have different laws of physics, different constants, even different dimensions, with ours just happening to be hospitable to galaxies and life. Yet the biggest question remains: what triggered inflation in the first place? Was it a quantum burp in a pre-existing spacetime, or did spacetime itself emerge from something deeper, perhaps a collision of higher dimensional membranes or a phase transition in a primordial quantum vacuum? The answer might lie in the quantum gravity realm, where inflation's energy meets the scale's chaos. Experiments hunting for primordial gravitational waves, ripples in spacetime from inflation's violent expansion, could soon provide clues. If detected, these waves would be a smoking gun, carrying imprints of the universe's first trillionth of a second. So while inflation explains so much, the universe's smoothness, its structure, even its sheer size, it also leaves us staring into an abyss of deeper mysteries. What came before? What lies beyond? For now, we're left with a humbling thought. Our entire observable universe might just be a speck in a far grander, far stranger reality, one where the rules we take for granted are just a local ordinance in an infinite cosmic metropolis. The idea of a multiverse isn't just science fiction. It's a serious scientific possibility, one that emerges naturally from the math of inflation and quantum mechanics. Picture an endless cosmic ocean where bubbles constantly form, each one a separate universe with its own unique physics. Some might expand and cool, giving rise to galaxies and life, while others collapse back into nothingness before they've even begun. Our universe, with its finely tuned constants that allow stars to shine and planets to form, could be just one lucky roll of the dice in an infinite casino of possibilities. String theory adds another layer to this mind-bending concept. With its landscape of possible vacuum states, each representing a different configuration of physical laws, it suggests that universes could exist where gravity is stronger, electromagnetism weaker, or even where time flows backward. Imagine a reality where the speed of light isn't a limit but a suggestion, or where atoms never learn to bond. These aren't just thought experiments, they're potential realities, each playing out in their own pocket of existence. The catch: we may never be able to visit them, communicate with them, or even prove they exist. The multiverse, by its very nature, might always lie beyond the reach of observation, making it as much a philosophical puzzle as a scientific one. Yet the implications are impossible to ignore. If our universe's laws seem suspiciously perfect for life, the multiverse offers an elegant explanation. In an infinite array of possibilities, some universes had to hit the jackpot. This is the anthropic principle in action. We find ourselves in a hospitable universe simply because we couldn't exist in the hostile ones. It's like waking up in a room with the thermostat set exactly to your comfort. Coincidence? Or just one of countless rooms, most of them freezing or scorching, with you lucking into the one that's just right. Some physicists argue that the multiverse is a cop-out, a way to dodge the hard questions about why our universe is the way it is. Others see it as the inevitable consequence of our best theories, a cosmic kaleidoscope where every twist creates a new pattern. The debate even spills into philosophy. If there are infinite versions of reality, does that make our choices meaningless? Or does it mean every possible version of us gets to live out every possible path? For now, the multiverse remains a shadow on the edge of science, too compelling to ignore, too elusive to confirm. But as we push the boundaries of quantum gravity, dark energy, and higher dimensions, we might one day find indirect clues, like anomalies in the cosmic microwave background or unexplained gravitational waves. Until then, the multiverse stands as a humbling reminder. Our universe, vast as it is, might just be a single note in an endless symphony of realities. Neutron stars are nature's most extreme physics experiments, cosmic pressure cookers where matter gets squeezed into forms so bizarre they defy earthly logic. Imagine taking the entire mass of our sun and crushing it down into a sphere the size of Manhattan. The result is a stellar corpse so dense that a single sugar cube-sized chunk would weigh as much as a mountain. But these ultra-compact objects aren't just curiosities. They're laboratories for studying nuclear physics under conditions we could never replicate on Earth. At their cores, neutron stars may harbor matter in its most exotic states. Under such unimaginable pressure, protons and electrons merge into neutrons, packing together until they nearly touch. But go deeper still, and even neutrons might break apart into their constituent quarks, creating a swirling soup of quark-gluon plasma, a state of matter that hasn't existed freely since the universe's first microseconds after the Big Bang. These extreme conditions let us test quantum, the theory governing how quarks interact through the strong nuclear force. It's like having a time machine to the universe's earliest moments, frozen in these celestial relics. When two neutron stars spiral together and collide, the cosmic fireworks illuminate another mystery, the origin of heavy elements. The violent mergers forge gold, platinum, and uranium in their aftermath, scattering these precious metals across galaxies. In 2017, astronomers witnessed such an event, detecting both gravitational waves and a gamma ray burst from the collision, confirming that neutron stars are cosmic alchemists, transforming ordinary matter into the elements that make up our jewelry, electronics, and even parts of our bodies. But perhaps the strangest neutron star feature is their crust. Just a kilometer beneath the surface, atomic nuclei get crushed into bizarre shapes, rods, slabs, or even nuclear pasta, where protons and neutrons arrange themselves into structures resembling spaghetti or lasagna sheets. This ultradense material is 100 trillion times stronger than steel, yet it can fracture under stress, creating that release bursts of X-rays detectable across interstellar space. From their role in seeding the universe with heavy elements to their potential as portals into quark matter, neutron stars are more than dead stars. They're stones for decoding matter's most fundamental secrets. Each pulsar's steady spin, each gravitational wave from a merger, brings us closer to understanding how extreme physics shapes the cosmos at every scale. Primordial black holes could be the universe's oldest hidden relics, tiny time capsules from the dawn of existence, formed not from collapsing stars, but from the unimaginable density fluctuations in the first moments after the Big Bang. Picture the infant universe as a seething, turbulent soup of energy, where pockets of spacetime briefly became so dense they pinched off into microscopic black holes, some no heavier than an asteroid yet as compact as a single atom. Unlike their stellar-born cousins, these ancient objects wouldn't require the death throes of massive stars to exist. They could have been forged in the chaos of creation itself, then scattered across the cosmos like cosmic breadcrumbs from the universe's first recipe. What makes them so tantalizing is where they might be hiding and what they could explain. If enough of these primordial black holes survived, they could account for dark matter's invisible mass, drifting unseen through galaxies like a swarm of ghosts. Some might even be passing through our solar system right now, too small and faint to detect with current telescopes. But there's a catch. If they're too light, they'd have evaporated long ago due to Hawking radiation, the quantum glow that causes small black holes to slowly dissolve. Those that survived would need to be at least as massive as a small moon, lingering in the shadows for billions of years. The hunt for these elusive objects has turned into a cosmic treasure hunt. Scientists scan for telltale flashes when a primordial black hole bends light from a distant star, a phenomenon called. Others analyze the ripples in gravitational wave detectors, hoping to catch the faint chirp of two tiny black holes merging. There's even speculation that some might have been captured by stars, orbiting invisibly in their cores and subtly altering their behavior. These hidden could explain mysterious stellar anomalies that defy conventional models. But the wildest possibility, some primordial black holes might not be black at all. If they're just the right mass, around that of a dwarf planet, they could be emitting Hawking radiation at visible wavelengths, glowing faintly like dying embers. Dubbed Hawking stars, these hypothetical objects would look like dim, cooling stars but harbor a black hole at their hearts. Spotting one would be like finding a cosmic Matryoshka doll, a star wrapped around a relic from the universe's birth. The implications stretch even further. If primordial black holes exist, they'd offer a direct probe into the conditions of the early universe, revealing details about inflation, quantum gravity, and the nature of spacetime itself. Their discovery would rewrite cosmology, bridging the gap between the quantum and cosmic scales in ways we've only dreamed of. So while they remain hypothetical for now, the search continues. Because finding even one would mean the universe has been keeping secrets far stranger than we ever imagined. The Milky Way isn't drifting through space aimlessly. It's being hauled toward something unseen at over 1 million miles per hour, caught in a cosmic current we can't fully explain. This invisible force, known as the Great Attractor, lurks roughly 250 million light-years away in the direction of the constellation Centaurus, pulling not just our galaxy but thousands of others in a relentless gravitational tide. The strangest part, we're staring straight at it, yet the Milky Way's own galactic disk, thick with dust and stars, blocks our view, like trying to peer through a blizzard to spot a distant mountain. What makes this mystery even more unsettling is the scale of the pull. The Great Attractor's influence spans hundreds of millions of light-years, suggesting it's not just a single massive object, but perhaps the heart of an enormous supercluster we've only begun to map. Observations reveal a dense knot of galaxies, including the Norma cluster, swirling around a common center of gravity. Yet even collectively, their mass doesn't fully account for the staggering force at work. It's as if we found a whirlpool in the ocean, only to realize the current is stronger than the visible water could possibly generate. This discrepancy has led scientists to speculate about darker, more exotic explanations. Could vast filaments of dark matter, threads woven through the cosmic web, be funneling galaxies toward this point like beads on a string? Or is the Great Attractor itself just a waypoint in an even larger flow, a single ripple in a universal current dragging us toward something far more colossal, like the mysterious supercluster, the largest known structure in our cosmic neighborhood? Some theories even flirt with the idea of primordial gravitational waves left over from the Big Bang, warping spacetime on scales we're only beginning to comprehend. The quest to unravel this enigma has pushed astronomy to its limits. Infrared telescopes like the European Space Agency's Gaia mission pierce through the Milky Way's dust veil, mapping the motions of millions of stars to trace the attractor's gravitational fingerprint. Meanwhile, radio telescopes chart the velocities of distant galaxies, revealing how they're swept up in this cosmic river. Each new dataset peels back another layer, yet the core question persists. Is the Great Attractor a sign of our incomplete map of the universe, or a clue to physics beyond relativity? One thing's certain, the universe is far from static. It's a dynamic, almost living thing, with hidden structures sculpting the paths of galaxies over billions of years. The Great Attractor reminds us that even as we peer deeper into space, the cosmos keeps its grandest designs just out of sight, urging us to look harder, think bigger, and embrace the humbling truth that some mysteries refuse to be solved with a single glance. At the heart of modern physics lies a schism so deep it threatens to fracture our understanding of reality itself. On one side stands general relativity, its masterpiece painting gravity as the curvature of spacetime by massive objects. On the other, quantum mechanics rules the subatomic realm, where particles flicker in and out of existence and entanglement defies classical intuition. Both theories work flawlessly in their respective domains, yet when they collide, like at the singularity of a black hole or the first moments of the Big Bang, the equations explode into nonsense. This isn't just a technical hiccup, it's a screaming alarm that we're missing something fundamental about how the universe operates. Enter the quest for quantum gravity, the monumental effort to stitch these two frameworks into a single, coherent theory. One leading contender, loop quantum gravity, proposes that spacetime isn't smooth and continuous, but woven from microscopic, indivisible loops. Picture the universe as a cosmic tapestry, where each thread is a quantum of spacetime so small that 1,000,000 billion could fit across a single atom. These loops intertwine to create the fabric of reality, with their vibrations giving rise to particles and forces. At the scale, a distance a trillion times smaller than an atom, spacetime might dissolve into a foamy, granular landscape where concepts like before and after lose meaning. Black holes could be knots in this quantum fabric, their singularities replaced by dense tangles of spacetime threads. Then there's string theory's approach, where gravity emerges from vibrating strings dancing in higher dimensions. But perhaps the most radical idea comes from holography, which suggests that gravity isn't fundamental at all, just a side effect of quantum information encoded on the universe's boundary. It's as if the 3D world we experience is a projection of data stored on a distant 2D surface, with gravity being the glitch that makes the illusion feel real. The stakes couldn't be higher. If quantum gravity is real, it would rewrite the story of the Big Bang, replacing the mythical singularity with a quantum bounce, a moment when the collapsing universe rebounded into expansion. Black holes might not be eternal prisons but gateways to new physics, their event horizons shimmering with quantum data. Even time itself could be an emergent property, something that crystallizes from deeper, timeless interactions. Yet for all its promise, quantum gravity remains frustratingly elusive. The energies required to probe the scale are quintillions of times beyond our particle collider's reach. So physicists get creative, searching for indirect clues in the cosmic microwave background's faint patterns, the precise timing of pulsar signals, or the quantum noise of gravitational wave detectors. Some even hope that microscopic black holes, if they exist, could reveal quantum gravity's fingerprints as they evaporate. What's clear is this: the universe doesn't owe us intuitive answers. The deeper we dig, the stranger reality becomes, and quantum gravity may be the key to unlocking its final secrets, or revealing just how much we still have left to learn. Time crystals sound like something ripped from a sci-fi novel, structures that pulse and oscillate without energy input, breaking one of physics' oldest rules, the inevitability of equilibrium. Unlike ordinary crystals, where atoms arrange themselves in repeating spatial patterns, time crystals repeat in time, oscillating between states indefinitely without losing energy. It's as if you pushed a pendulum once and watched it swing forever, untouched by friction or decay. When Nobel laureate Frank first proposed the idea in 2012, many physicists dismissed it as impossible, a violation of thermodynamics' sacred laws. Yet just 5 years later, labs created them using chains of ions or diamond defects, proving nature had yet another trick up its sleeve. What makes time crystals so revolutionary isn't just their defiance of classical physics, it's their potential to rewrite the rules of quantum computing. Traditional quantum bits or qubits are fragile, collapsing at the slightest disturbance. But time crystals are inherently stable, their rhythmic patterns resistant to entropy. Imagine a quantum computer where information isn't stored in delicate superpositions, but in the unshakable beats of a time crystal's dance. Researchers are already exploring how their predictable oscillations could synchronize qubits, reducing errors and bringing fault-tolerant quantum computing closer to reality. But the real cosmic twist, time crystals might not be confined to labs. Some theories suggest they could form naturally in extreme environments, perhaps near neutron stars, where gravitational waves and magnetic fields churn spacetime into bizarre configurations, or deep inside exotic materials subjected to relentless quantum fluctuations. If they exist out there, they'd be more than curiosities. They'd be evidence of entirely new phases of matter, ones that don't just exist in time but are fundamentally shaped by it. The most tantalizing question is whether time crystals could redefine time itself. In its relativity, time is a dimension, a backdrop against which events unfold. But time crystals treat time as an active participant, their structure emerging from its flow. Could they hint at a deeper connection between time and quantum mechanics, a bridge between the microscopic and cosmic? For now, they're a laboratory marvel, but their implications ripple far beyond, into black holes, the early universe, and perhaps even the nature of reality. One thing's certain. In a universe where matter can tick like a perpetual clock, the line between science and science fiction has never been thinner. Even at absolute zero, when all thermal motion should grind to a halt, the universe refuses to sit still. Quantum mechanics reveals a startling truth. There's no such thing as true emptiness. Every cubic centimeter of space, no matter how cold or dark, hums with an irreducible energy, zero-point energy, the universe's baseline buzz. Picture a piano string vibrating even when untouched, or a glass of water that can never be perfectly still, no matter how carefully you set it down. This isn't just theoretical. Lasers, superconductors, and even the Hubble effect, where metal plates mysteriously pull together in a vacuum, all bear witness to this restless energy simmering beneath reality's surface. What's truly mind-bending is the scale of this hidden power. Calculate the zero-point energy in a single swath of space, and the result could power entire cities if we could tap into it. The problem: this energy is locked in a quantum tug-of-war, with particles and antiparticles flickering in and out of existence too quickly to harness. It's like trying to catch individual raindrops in a hurricane. Yet the potential is so staggering that scientists and engineers keep probing the edges of possibility. Imagine spacecraft propelled by vacuum energy, or batteries that draw power from the fabric of space itself. NASA's Breakthrough Propulsion Physics program once explored these very ideas, though the challenges remain monumental. Then there's the cosmic connection. Some theorists suggest zero-point energy isn't just a quirk of quantum mechanics. It could be the engine behind dark energy, the mysterious force accelerating the universe's expansion. If the vacuum's energy density isn't perfectly balanced, its slight pressure might be pushing galaxies apart. This would mean the fate of the cosmos hinges on the same quantum whispers that make empty space seethe with potential. But here's the catch. Zero-point energy also threatens to unravel physics as we know it. Sum up all these quantum fluctuations across the universe, and the total energy should curve spacetime into a black hole. The fact that it doesn't implies either a cancellation mechanism beyond our current theories, or that we're fundamentally misunderstanding the vacuum's true nature. So is space an infinite reservoir of untapped power, or a cosmic mirage teasing us with energy we can never truly grasp? The answer might rewrite not just our technology, but our very understanding of existence. One thing's certain, the universe's silence is an illusion. Beneath the apparent stillness, it's a thunderstorm of potential, waiting for us to learn its language. Antimatter is the universe's greatest vanishing act, a cosmic magic trick where half the ingredients for existence seem to have disappeared without a trace. For every electron, there's a positron. For every quark, an antiquark. These mirror-image particles are identical to their matter counterparts in mass, but opposite in charge, annihilating each other in a flash of pure energy when they meet. Yet here's the puzzle. If the Big Bang created matter and antimatter in equal amounts, why is the cosmos filled with galaxies, stars, and planets instead of just light? The fact that we exist at all suggests something tipped the scales in matter's favor, a 1 in a billion imbalance that allowed a tiny fraction of particles to survive annihilation and build everything we see. CERN's ALPHA experiment is hunting for answers by trapping atoms, antimatter's simplest form, in magnetic bottles, probing whether they behave identically to regular hydrogen. Even the slightest discrepancy could reveal why matter won the cosmic lottery. One leading suspect is CP violation, a subtle quirk in particle physics where matter and antimatter don't quite mirror each other. Think of it like shaking two nearly identical snow globes, only for one to settle slightly faster. In the early universe, this tiny asymmetry might have allowed matter to dominate, with antimatter vanishing into energy. But the known cases of CP violation, like those observed in kaon and B-meson decays, aren't nearly enough to explain the universe's matter surplus. Theories abound. Some suggest antimatter wasn't destroyed but exiled, segregated into distant regions of space by primordial forces, forming hidden anti-galaxies beyond our observational horizon. Others propose that gravity treats antimatter differently, causing it to repel rather than attract, though experiments like AES at CERN aim to test this by dropping in a gravitational field. Then there's the neutrino factor. These ghostly particles might hold the key, as their slight preference for matter over antimatter could have cascaded into the imbalance we see today. But the boldest idea, antimatter might not be missing at all. If some primordial process transformed antimatter into dark matter, a shadowy, non-annihilating form, it could mean the universe's two biggest mysteries are two sides of the same coin. Until we catch a whiff of indistant space or unlock gravity's secrets with anti-atoms, the question lingers. Is antimatter the universe's lost twin, or did it never stand a chance to begin with? The answer won't just rewrite physics. It'll tell us why there's something rather than nothing at all. Gravitational waves are the universe's hidden language, whispers of spacetime itself bending and stretching under the weight of cataclysmic events. When first predicted their existence in 1915, they seemed almost too strange to be real. Ripples in the fabric of reality, traveling at light speed from collisions so violent they momentarily warped the cosmos. For a century, they remained theoretical, until September 14, 2015, when the Laser Interferometer Gravitational Wave Observatory, or LIGO, caught the faint echo of two black holes merging 1.3 billion light-years away. That signal, lasting less than a fifth of a second, marked the dawn of an entirely new way to observe the universe. What LIGO and its European counterpart, Virgo, detect isn't light or radiation, but the literal stretching and squeezing of spacetime. Picture dropping two pebbles into a still pond. The ripples they create are gravitational waves, but instead of water, they distort the very dimensions we exist in. These detectors work like cosmic microphones, with laser beams bouncing down 4-kilometer-long arms, measuring changes smaller than 1,000th the width of a proton. When a wave passes, one arm stretches while the other compresses, and that minuscule shift betrays the universe's most violent secrets. The events that generate these waves are almost unimaginable. Black holes spiraling into each other, neutron stars tearing each other apart. Each collision unleashes more energy in gravitational waves than all the stars in the observable universe emit as light. In 2017, LIGO and Virgo detected a neutron star merger, an event that not only sent gravitational waves but also a gamma-ray burst, and a flash of light so intense it forged heavy elements like gold and platinum. For the first time, astronomers could hear and see the same cosmic explosion, ushering in multi-messenger astronomy. But the most thrilling possibilities lie ahead. Gravitational waves could reveal primordial black holes from the dawn of time or cosmic strings, hypothetical defects in spacetime left over from the Big Bang. They might even expose flaws in relativity, hinting at quantum gravity's influence in extreme environments. And as detectors grow more sensitive, with plans for space-based observatories like LISA, we'll tune into frequencies that could uncover supermassive black holes merging at the hearts of galaxies, or the faint hum from the universe's inflationary infancy. This isn't just about observing the cosmos, it's about feeling it. Gravitational waves let us sense the universe's vibrations, turning silent voids into symphonies of collision and rebirth. Every ripple carries a story, and we're just learning how to listen. The cosmos should be teeming with life. With hundreds of billions of galaxies, each hosting countless stars and planets, the numbers alone suggest we shouldn't be alone. And yet silence. No signals, no spacecraft, no cosmic greetings. This eerie absence is the Fermi paradox, a puzzle that grows more unsettling the deeper we look. If intelligent life is even remotely common, why does the universe feel so empty? The answers we've proposed range from sobering to downright chilling. One possibility is that life is extraordinarily rare, that Earth is a cosmic fluke, a perfect storm of conditions so unlikely it's barely repeated. Think of it like shuffling a deck of cards and getting the same order twice in a row. The ingredients for life, liquid water, stable orbits, protective magnetic fields, might align so infrequently that civilizations are scattered across galaxies like desert oases. But this raises another question. If we're alone, what does that mean for our future? Without others to learn from or compete with, humanity's survival becomes both a triumph and a terrifying responsibility. Then there's the darker alternative. Advanced civilizations don't last. Maybe technological progress inevitably leads to self-destruction through war, environmental collapse, or uncontrolled artificial intelligence. This great filter theory suggests that something stops intelligent life from reaching the stars, and we might not yet know if we've already passed it or if it still lies ahead. The ruins of ancient alien empires could be littered across the galaxy, their signals long faded into the cosmic background. But what if aliens are out there, just nothing like we expect? Quantum physics opens doors to bizarre possibilities. Advanced beings might communicate through entangled particles, sending messages instantly across light years without any detectable radiation. Or they could exist in higher dimensions, their presence as invisible to us as shadows on a wall. Some theorists even speculate that civilizations could transcend physical form, uploading their consciousness into synthetic realities or dark matter structures we can't perceive. The silence might also be deliberate. Imagine a universe where predatory civilizations lurk and the only safe strategy is to stay hidden. Or perhaps we're like ants in a rainforest, unaware of the towering beings around us because we lack the senses to notice. Our radio signals have only traveled 100 light years, a tiny bubble in a galaxy 100,000 light years wide. To an older, wiser species, we might still be too primitive to contact. Yet the most profound answer could be the simplest. we're looking at the wrong time. Civilizations might rise and fall in cosmic blinks. They're too short to overlap with ours. The universe is ancient, 13.8 billion years old, and we've only been listening for a century. It's like tuning into a radio station for 3 seconds and concluding no one's broadcasting. The truth might not be that we're alone, but that we're late or early to the party. So while the stars remain quiet, their silence speaks volumes. Every unanswered signal, every empty exoplanet survey, forces us to confront fundamental questions about life, intelligence, and our place in the cosmos. The Fermi paradox isn't just about aliens. It's a mirror reflecting our hopes, fears, and the fragile rarity of existence itself. And until we find proof otherwise, the universe keeps its secrets close. What if your thoughts aren't just electrical impulses flickering through neurons, but quantum ripples woven into the universe itself? This radical idea, quantum consciousness, dares to suggest that the human mind operates on the same strange rules as subatomic particles, blurring the line between brain and cosmos. At the heart of this theory lies the microtubule, tiny protein structures inside neurons that some researchers believe could host quantum vibrations. These vibrations, fragile and fleeting, might orchestrate our awareness like a symphony of microscopic waves. If true, consciousness wouldn't just emerge from the brain, it would be a cosmic phenomenon, as fundamental to reality as gravity or light. The implications are staggering. Consider the double-slit experiment, where particles behave as waves until observed, as if choosing their state when measured. Some theorists argue this quantum weirdness mirrors how our minds collapse possibilities into perceptions, shaping reality by the act of observation itself. Could consciousness be the universe's way of observing itself, a feedback loop where mind and matter intertwine? Philosophers like Alfred North Whitehead hinted at this centuries ago, suggesting reality is a network of experiences rather than inert objects. Now, modern scientists like Sir Roger and anesthesiologist Stewart have revived the idea with their orchestrated objective reduction theory, proposing that quantum processes in microtubules generate consciousness, and that these processes might even survive death, hinting at a quantum basis for near-death experiences. Critics, of course, dismiss this as speculative. The brain is warm, wet, and noisy, far from the pristine labs where quantum effects are typically observed. Decoherence, the tendency for quantum states to collapse in chaotic environments, should render such processes impossible in our skulls. Yet defenders counter with surprising findings. Photosynthesis relies on quantum coherence in sunlit plants, and bird navigation may harness quantum entanglement in their eyes. If biology already exploits quantum tricks, why not the brain? The most profound question isn't just whether quantum consciousness is real, it's what it would mean if it were. If our minds tap into quantum layers of reality, could telepathy or precognition have a scientific basis? Might the universe itself possess a form of proto-consciousness, with galaxies and atoms participating in a vast, interconnected network of awareness? These ideas flirt with spirituality, but they also push physics into uncharted territory. The mystery of consciousness remains one of science's last great frontiers, and whether quantum mechanics holds the key or not, the pursuit forces us to confront a humbling truth. The universe might not just contain minds, it might, in some deep way, be a mind. And that changes everything. Simulated reality. Are we in a quantum computer? The simulation hypothesis suggests our universe might be an advanced civilization's creation. Quantum indeterminacy could be processing limits, and glitches might reveal the code. While speculative, it raises profound questions about existence. Is reality base level, or are we characters in a cosmic simulation? Imagine waking up one day to discover your entire life, every memory, every sensation, was just lines of code in an advanced quantum computer. This isn't the plot of a sci-fi movie. It's a serious argument debated by physicists and philosophers alike. The simulation hypothesis proposes that our universe, with all its galaxies, black holes, and coffee shops, might be an artificial construct, a digital playground built by a civilization so advanced, their technology is indistinguishable from nature itself. At its core, this idea hinges on a simple premise. If consciousness can be replicated or uploaded, then statistically, the odds favor us living in a simulation rather than base reality. After all, how many real universes could there be compared to the countless simulations a single advanced civilization might run? Quantum mechanics adds eerie weight to this theory. Why do particles exist in fuzzy superpositions until observed? Some theorists suggest it's not a fundamental law of nature, but a rendering trick, a way for the simulation to save processing power by only calculating definite states when necessary. Think of it like a video game that doesn't render distant mountains until you look at them. Quantum indeterminacy, entanglement, even the length, the smallest possible unit of space, could all be artifacts of a finite computational system. Even glitches in our reality, or unexplainable cosmic anomalies, might be tiny cracks in the code, moments where the simulation stutters. But how could we ever test such a wild idea? Some scientists propose looking for in the fabric of reality. If spacetime has a finite resolution, high-energy cosmic rays might reveal jagged edges in their behavior at the smallest scales. Others suggest searching for mathematical constraints in physical constants, evidence that the universe's rules were programmed rather than emergent. There's even a fringe effort to hack the simulation by exploiting quantum loopholes, attempting to inject custom code into reality itself. Of course, not everyone buys into this digital metaphysics. Critics argue that simulating every particle in the universe would require more energy than the universe itself contains, unless the simulation is vastly, running only what's observed. But that raises another question: who's observing the unobserved parts? And if we're just characters in someone else's simulation, does our quest for meaning lose its weight or gain a new layer of irony? The simulation hypothesis forces us to confront the nature of reality itself. Whether we're in a quantum computer or not, the mere possibility changes how we see existence. It blurs the line between science and philosophy, between creator and creation. And if one day we discover irrefutable proof, it wouldn't just rewrite physics, it would redefine what it means to be alive. After all, in a simulation, even the question, "Are we real?" becomes part of the code. From the quantum foam's seething dance to the holographic threads that might weave our reality, we've journeyed through a cosmos where the smallest scales hold the grandest blueprints. Every flickering virtual particle, every entangled photon, every whisper of dark matter isn't just a footnote in physics, it's a brushstroke in the universe's masterpiece. Think of it like a cosmic tapestry. Tug one invisible thread at the quantum level, and the ripple echoes across galaxies, bending light, sculpting matter, even steering the fate of time itself. And yet, for all we've uncovered, the deeper we dig, the more the universe resists simple answers. Black holes dissolve into paradoxes, dark energy defies calculation, and the multiverse teases us with realities just beyond reach. But that's the thrill of it. Science isn't about collecting final answers, it's about chasing better questions. Every time we build a more powerful telescope or a more sensitive detector, the cosmos hands us a fresh puzzle, a new layer of its infinite onion. Consider this: the very atoms in your body were forged in the hearts of long-dead stars, their journeys orchestrated by quantum fluctuations in the universe's first moments. You're not just an observer of this cosmic story, you're a living, breathing part of it. So as we stand on the edge of breakthroughs, whether it's decoding quantum gravity, spotting Hawking radiation, or glimpsing parallel universes, remember that curiosity is our superpower. The universe isn't just out there, it's in the questions we dare to ask, the mysteries we refuse to take for granted. So keep looking up, but don't stop there. Look down, look inward, look beyond. Because the next great revelation might not come from a distant galaxy, but from the quantum whispers hiding in plain sight. The cosmos isn't finished surprising us, and neither are we.